Today we're going to take a look at section 9.2. It's called Multistage Experiments. In section 1, every problem that you looked at had the commonality that when you selected something from the sample space, you were only doing it one time. You were selecting one number out of 10 numbers, or one ball out of the 12 balls, or one card out of the 13 cards. You're only making one choice. So what's going to happen in this section is that you're making more than one choice. That's the multi-stage part. So you select one card and then you select another card. So how is that first card going to affect the choice of the second card? That kind of a thing, okay? So in particular, in this section, and this is not the only way to do the problems, I understand that, but it is the way that I'm going to show you because it's very nicely working all the time for you. And these are called tree diagrams. Tree diagrams are a sample space model where each outcome is designated by a separate branch. I'll draw you one in just a moment after I do the next two on this slide. One-stage experiments, which is what you did in 9.1, are experiments that are over after one step. You only made one choice. Two-stage experiments are experiments that are over after two steps. So when we talk about multi-stage experiments in this section, it's going to be two or more steps. So in particular, you would have something in a tree diagram that looks like this. Working from left to right's one way to draw them. If you really want to, you can draw them top down. That's okay too. It doesn't matter to me. I tend to draw mine left to right. But let's say, for example, that we were working with a problem from the last section where you're wanting to know, what's the probability that something turns out to be even? Well, you have the possibility that you have even answers and the possibility that you have odd answers. And this would be one stage, right? Well, what if you want to know what's the probability that I get two evens or two odds? Or what do I want to know if I have like an even and an odd, if I pull these numbers out of this basket or whatever? Well, what it ends up looking like is another set of branches. Okay? And then we write again on the end what's going on in the outcomes we're looking at. So as you see along each branch, you can see the full outcome. So this would be, experiment stage number 1, right? Multi-stage first stage. So I get an even or an odd. After I get an even, I draw again. Well, I could get another even, so I'd have an even and an even. Or I could get an even and then an odd. Or I could have gotten an odd the first time I made my, selection out of the hat, and then I got an even the second time, or I got an odd the first time, I got an odd the second time. And depending on what we're working with, and there's lots of ways to work with it, will depend on the probability of each of those things. So if we were looking at the sample space that Kurt mentioned, where it was the numbers 0 through 9, well, it's a 50-50 chance that you're going to choose an even or an odd, right? 5 out of 10 chance. But then it matters. Did you replace the number back in the basket before you made your second choice? Or did you keep the number? Because then it changes the possible outcomes. So we're going to take a look at that. A couple more things before we do a full-out example, which is example number 1, that we need to have under our belt. Whoops. Multiplication rule. The multiplication rule for tree diagrams says that for all multi-stage experiments, the probability of an outcome along any path of the tree diagram is equal to the product of the probabilities along the path. And a reminder note, I kind of alluded to this earlier, but a reminder note, I expected to see a tree diagram or something equivalent, and I'll show you an example of something equivalent on one of our problems today. For each of your problems, this is what you would have your students do. So there may be situations where you're like, I don't need to draw a tree diagram. I can do it in my head. And you maybe can. Your students probably can't. So I want to make sure that you're able to show your students what you would expect from them if they were doing outcomes in probability. All right. Back in section 9.1, you encountered the phrase mutually exclusive. Is that true? Yes? And mutually exclusive was the idea of having no overlap. Mutually exclusive is a phrase that's commonly confused with the next one. The next one's called independent. They do not mean the same thing. Independent means that the event in which the occurrence of one, it's an event in which the occurrence of one event has no influence on the outcome of the second event. Okay, so imagine if you were to roll a die, right? Standard 6-sided die. And you rolled a 6. Well, what's the likelihood that you're going to roll a 6 the next time? The same as it was the first time. The first roll of the 6 has absolutely no bearing on the outcome of the second roll. If I get pregnant and I have a boy, and then I get pregnant a second time, what's the chances that the next child's going to be a boy? Same as they were the first time, right? It has absolutely no effect on the second time you do it. Now imagine back here where I was talking about putting numbers in a hat. Whoops, right here. If I put the 10 numbers in a hat, 0 to 9, and I draw out an even number, and I keep it, how many even numbers are still in the basket? 4, right? There were 5 originally, and I drew 1 out. So that draw, where I keep the number, affects how many now I would be drawing from on the second time around. It matters. That would not be an independent event. However, if I put the number back into the basket and there's the same 10 numbers the second time around, reach in and draw it again, that'd be independent. So when I replaced it back in, that's an independent event because the outcome, I have the exact same sample space I had the first time. But if I kept the number out, it changed the sample space. What I have to choose from is now different than what I had to choose from originally. Okay, so that's the difference between independent versus dependent events. Do they depend on one another? And then this theorem 9.7 tells you exactly what that does in terms of like a formula. The probability of event 1 and event 2 occurring is the probability of event 1 times the probability of an event 2, if they're independent. That is the kicker here. They have to be independent events or this does not hold true. All right, so let's take a look at example number 1. And the first thing I want us to talk about, just because we've talked about this language, is whether or not the event is independent. An executive committee consists of 10 members, 4 women and 6 men. 3 members were selected at random to attend a meeting in Hawaii. Who wants to go? Me and Emily and Alicia, we're going to go to Hawaii. The rest of you can just stay here because we were the first ones who raised our hand, right? No, like they're going to do it at random, right? They're going to do it at random. So what do we have to do to figure out what's going on? Well, we've got some questions on the next page. But the first thing I want you to think about is the event mutually exclusive? How many people are going? 3. So if you imagine like a bucket of people's names, we're going to reach in the bucket 3 times and pull out a name, right? And we're actually only caring about the gender. Do we have men, women, or both going? That's the question's going to lead to in a minute here. But the question is it independent? Are each of the draws of a name out of the hat an independent event from the previous draw? What do you think? Emily, what did you say? You said no. You're correct. It is no. What were you thinking when you thought it was no?
Well, you said that you're independent, like you have to put it back in.
Yeah. And it wouldn't make sense to put the person's name back in, right? They're already going. Yeah. So this is an example of something that is a non-independent situation. The first person's name that pulls out is going to affect the future draws because they can't be drawn again. Wouldn't make any sense. So we are going to draw 3 times. You have space on this first page. So before we go to the next page and look at the questions, we're going to draw a full tree diagram for what's going on here, okay? So the first thing that happens, because it's all talking about gender, men versus women, is that we actually only have 2 possible outcomes if that's the only consideration we're looking at. Does that make sense? 2 possible outcomes. We either draw a man's name out of the hat or a woman's name out of the hat. So you can call them male, female, man, woman. I don't care. I'm going to go with male, female. And we're going to go with that. Male, female. The first time I reach in the hat and I draw the names, what is the likelihood that I draw out a man's name? 6 out of what? 6 out of 10. So along the branch, we're going to write the probability of that outcome. Okay, we're going to write the outcome at the end, male. We're going to write the probability along the branch. It's a 6 out of 10 chance that that happens. So what's the chance that I pull out a female's name? 4 out of 10. You got it. But once I draw whatever I draw out of the hat, how many names are still in the hat? 9. So the next time I write down probabilities, I'm not going to be writing out of 10. There's not 10 names in the hat anymore. There are only 9. So after the first draw, we have one more draw. Male versus female. And the outcome can be male or female regardless of what was drawn the first time. I still have enough of them in the basket for that to be a realistic thing. I'm going to have to shrink my picture. I made it too big. Let's look at the men. Okay, so if I'm going along the first branch, right up here, I know that I've drawn one man's name out. So how many men's names are left in the basket? 5. Out of how many names? 9. How many women's names are left in the basket? 4 out of 9. Now notice each branch, each pair of branches that are paired together, they add up to 1, right? It's always going to happen. So these two numbers, they add up to 1. These two numbers, they add up to 1, right? 4 out of 5, 4 out of 9, 5 out of 9. So let's look down here at the bottom branch, this one over here. How many male names are still in my basket? 6 in that case, right? Out of how many names total? 9. How many women's names are still in the basket? 3 out of 9. All right. So that gets me 2 of the people, right, that are going to Hawaii. And then I need one more set, or one more choice, because I'm supposed to be taking 3 people to Hawaii. Okay, they end the same way, male, female, male, female. So it looks like that. Okay, so along the top branch, the very, very top branch, so far right there, I have chosen 2 men's names, right? So how many men's names are left in the basket, whatever? 4. How many names are total left in the basket? Yeah, so it's 4 out of 8. So if there are 4 out of 8 male names in the basket, how many female names are in the basket? 4 out of the same 8, right? Because they have to add up to the full 8. All right, so let's look at the next branch. The next branch, I chose a man and then a woman, right? That's where we are when we get to this piece right here. I've chosen one man name, one woman name. So how many men's names are still left in that scenario in my basket? 5. Out of how many names? 8. How many female names are left in the basket? What is it?
3.
It is 3, because I chose one of them already, so 3 out of 8. I'm kind of running out of space. Let me move these over a little bit. Here we go. How about the next branch? This branch I chose a female and then I chose a male. Well, that's the same as the branch before, right? I just did it in the other order. I did male then female, and this one's female then male. So those probabilities should be the same as the ones before. 5 names left are men's names, 3 names left are women's names. So I have 5 out of 8 and 3 out of 8. Does that make sense for everyone? Cool. All right, last one. On the last one, I have chosen 2 females so far. So how many men's names are still left in the basket? All 6 of the original out of 8. How many women's names are still left in my basket? 2 out of 8. Okay, so this is a completely fleshed out, finalized, if you will, Venn diagram. I didn't mean that right. Tree diagram is what I meant to say, tree diagram. So let's look at the questions that are on the following page. I've already alluded to what they were going to ask us, but let's take a look at them together. Part A says, what is the probability that all 3 selected are women? So looking back at my diagram, what am I looking for on my diagram to answer that question? The only females row, which is where? Yeah, it's the very bottom one. So this very bottom row right here is going to answer the question to part A. Does that make sense to everyone? Okay, and we're going to do that based on what we said over here in Theorem 9.6. The way that we get that outcome to happen is that we multiply every piece of the branch's probabilities together. So over here I need to multiply 4 over 10, 3 over 9, and 2 over 8. So 4 over 10 times 3 over 9 times 2 over 8. Okay, so we've done a lot with fractions. We did a whole section, a whole chapter on them. You're welcome to multiply across the top, multiply across the bottom, and then reduce at the end if you wish. Kind of like reducing in the middle because then my numbers stay smaller. For example, the 4 and the 10 to start with are not reduced, so I can change those to 2 and 5, right? I mean, that works nicely. The 3 and the 9, same thing. I can change that to a 1 and a 3. The 2 and the 8 even are 1 and 4. So already I've changed the problem to be much smaller numbers. I have 2 over 5 times 1 over 3 times, 1 over 4. Again, if you want to multiply across the top, multiply across the bottom, and reduce, you can. There is one more reducing step if you want to that you could do. Do you guys see what it is? The 2 right here and the 4 right here, you could reduce those because one's in the numerator, the other one's in the denominator, to giving you a 1 and 2. If you don't see that, it's not a problem. You'll get there eventually because you're going to reduce it at the end. You'll end up getting 1 out of what? 30. 1 out of 30. That is not very likely, right? It's not very likely to happen. 1 out of 30 chance that we end up with 3 females going on this trip. B is a little trickier because there's more than one way to do the problem. So B says, what is the probability that at least one man is selected? So let's go over to your picture. If I want at least one man to go on the trip, or I'm trying to find the probability that that happens, what would that look like on this diagram? There's a bunch of different routes you could take, right? How many? More than 3. Okay, Emily, you're right. Can you describe a little bit more about how you got there?
So there's only one outcome that's all female, and you just have to have at least one. So every other outcome has at least one.
Okay, so I'm going to highlight them to show what you're describing. Emily says that every other outcome along my diagram has at least one man on it. Are you guys with me on that? Every other outcome has that. All the yellow ones end up having at least one man going on the trip. So here's the first way to do the problem. That's the hard way, and then we're going to do it the way Emily suggested because her way is definitely easier. You could multiply every single one of those other 7 branches. There are 7 other branches out, just like we did the last problem. And then add those 7 different answers together. So it'll be an 8-part problem, wouldn't it? Multiply 7 things out and then add those 7 things together. And that'd be your answer. But the reality is, and what you learned in the last section, is that within a sample space, you have 100% of the outcomes. Like everything that I've drawn here is all possible ways this problem could work out. Agreed? And all of them have to add up to 100% or the probability of 1. So instead of adding up the probability of all other 7 branches, which is the way we just talked about it, instead we could do 1 minus the probability of the all female branch. Because that's the only one that doesn't have the desired outcome, the one we just found from part A. So instead of having a 7-part problem, well, it was 8, 7 multiplications and then an addition at the end, I could just do 1 minus 1 over 30. And it's a 1-part problem instead of an 8-part problem. Because the reality is that what we found is that the probability of the 7 branches, that's my desired outcome, plus the probability of the all-female branch has to equal 1, because it's all 8 branches represented. So that's what I'm using to do this. So what is 1 minus 1 over 30? 29 over 30, right? So there's a 29 over 30 chance that at least one man goes on the bus on the trip to Hawaii. Is that okay? All right, example number 2 is an example of one where a tree diagram, you could do that, but there's another very similar argument, and you could do it in a slightly different way, but it still shows work. It's not just randomly pulling nothing out of the air kind of thing. So let's take a look at it. Box contains 5 slips of paper, numbered 4, 6, 7, 8, 9. A player reaches into the box and draws out 2 slips. Okay, so it's a 2-step statement, right? They draw 1 out, they draw 2 out. That's the same thing as drawing 2 out at the same time. It's exactly the same thing. And then they add the results together. Okay, whatever 2 numbers they get, they add them together. If their sum is even, they win, and if their sum is odd, then they lose. So one way of doing this problem is to simply write out all the possible outcomes instead of a tree diagram, which shows the possible outcomes that could happen. For example, if I draw out a 4, what else could I draw out? A 6. So 4 and 6 give me 10. But if I drew out a 4, what else could I draw out? A 7. 4 and 7 would give me 11. What if I draw out a 4 and an 8? I get 12. Or I could draw out a 4 and a 9, and I would get 13. And that's all the ways that I could draw out a 4 and combine it with anything else, right? So I've written down all the combinations, all the options that have a 4 with them. So let's just say that I don't need to write out any more 4s because I've written them all out. So maybe I didn't draw any 4s out. Maybe I started with a 6. Well, I don't need to do 6 plus 4 because I already did that outcome, right? But I could do 6 and 7, which is 13, or 6 and 8, which is 14, or 6 and 9, which is 15. And that's all the additional ways that I could group a 6 with something. So what else do I need to write down then? 7 plus 8 and 7 plus 9. So 7 plus 8 is 15. 7 plus 9 is 16. And I believe there's one more. Yeah, 8 and 9, which would give me 17. So it didn't write out a tree diagram, but it did write out every possible thing that could happen, right? So it's the equivalent of having a tree diagram written out. Now it says what's the probability a player wins. So go back and look. What did it say I have to do to win? Has to be even. So count how many do I have that are even? 4 is what I have. Is that right? 4. 4 out of how many possible outcomes? 10. And we're always going to reduce. What is 4 out of 10? Yeah, 2/5. 2/5. What if you wanted them to be multiplied? Will it change it? So we will pick up on part B next time on this lesson. Have a great evening.